We've been looking at the noise cancelling LNA since last class. Before we go ahead with this, are there any questions based on what we discussed yesterday? Let's quickly review so that we can come to a point where we can go ahead with the circuit. So what we wanted to do was take an LNA, which may be noisy. There are several LNAs that are noisy, right? But broadband, right? The one LNA that we found which gave you really low noise figures had very narrow band operation. So you directly traded off bandwidth of operation versus noise figure. Okay. So what we thought was, let's take one of the noisy LNAs, which is hopefully already broadband, okay, and try to do broadband noise cancellation through an auxiliary amplifier. So you take a second amplifier, sense the noise somewhere either at the input or somewhere inside the circuit. I have shown it as coming from the input. It could be somewhere inside the circuit also. I could have sampled the noise from somewhere inside the circuit. I say sampled, take a portion of the noise and gain it up appropriately. So with the right gain and phase, I need to add it at the output so that the noise of the original noisy broadband LNA is cancelled over as wide a bandwidth as possible. Right? What am I hoping to achieve? I am hoping to achieve a broadband low noise amplifier which still preserves the input match over a very wide band of operation, preserves low noise over a very wide band of bandwidth of operation. Okay? Then, of course, the additional points to remember are that the auxiliary amplifier should not disturb the input match. Okay, we have shown it here as being tapped from the input, so it should not disturb the input match. If it is being tapped from somewhere inside the circuit, same constraint, right? As long as it doesn't change the input impedance, you're okay. Number two, that should be extremely low noise, right? That should be very low noise so that you don't end up with a broadband noise cancelled noisy LNA. Okay. We started off with the common gate LNA because we know it's fundamentally broadband. We know its noise cannot be pushed down beyond a certain point. Okay, so we took that noise. We found that the output noise is minus IN1 by 2 times RD. Okay. The noise at the input is plus IN by 2 times RS. Okay, this is what we know so far. Okay, and we need to design the second A2. Okay, so first question. So I think we also found, I think we kind of concluded that this particular LNA, in this particular LNA, instead of subtracting the output, we'll just take the output as a differential output so that you have an inherent balance operation. So let us quickly write down what we have here. We have your common gate LNA. Okay. Vn in is In1 Rs by 2. Vn out is minus In1 RD by 2. Okay, so this much we know. I'm going to take an auxiliary amplifier. In this case, I'm tapping it directly from the input. This is A2. And my output is going to be seen differentially. So let us say this was some VNO2. VNO2. Okay. First, so VOD is V plus minus V minus. So first question, what should be the magnitude and phase of VNO2? Let's assume for now that A2 is noiseless. I want zero noise at the output. So of course, we want VODN correct? We know that V plus N is minus IN1 RD by 2. So this should also be, is that obvious? Okay, it should have the same, it should look like a common mode noise, so that when you subtract the 2, it will get cancelled. Okay, so what should be the value of A2? A2 should now be RD by RS with a negative sign. Does this make sense? If AD is RT by RS, so IN plus IN1 RS by 2 times minus RD by RS will basically give you minus IN1 RD. Okay. So we want a broadband low noise amplifier that gives you again minus RD by RS. Okay. So first question, what amplifier structure should we think of? So remember that the three most popular amplifier structures are the common gate, common drain, and common source. The common source amplifier can give you high input impedance, which is what we want here. If you put in a common gate structure, it will give you low input impedance. It will change the input impedance from 50 ohms to something else. We do not want that. So common gate is ruled out. What about common drain? Also ruled out because it has no gain. It has no voltage gain. So it is natural that you want to use the common source. So our problem now boils down to building a common source amplifier that has, of course, high input impedance, and that's okay. High input impedance means it should not be a degenerated amplifier. You should just be looking into the gate capacitance. You need to make sure that that gate capacitance is as low as possible. Okay. So Zn tends to infinity means you choose a common source amplifier with very small W over L. What else do you need? So this will take care of Zn. This will take care of preserving Zn. What else do you need to do? What are the two things you needed from the, or three things you needed from the auxiliary amplifier? You needed high input impedance. You needed a gain of RD by RS. How do you build a gain of RD by RS? Well, the gain of the common source amplifier is what? Is minus GM RL. I'll call that some RL. Okay. So it has the right sign. You wanted a negative gain, right? That's also great. All you have to do is set the GM RL of the common source amplifier. So set GM RL equals RD by RS. Okay. What else do you need to do? Low noise, right? So 0.1, 0.2, 0.3. What is the input referred noise of a common source amplifier? Right now we are saying it's a resistive load. It is some GMRL, right? What is the input referred noise? Do you remember? Well, in this course, we do not write it as 8 kT by 3 GM. We write it as 4 kT gamma GM. Okay. So what is the total output noise? It's 4 kT gamma GM delta F. That is the drain noise of the transistor. Plus, look at the short circuit current. So you also have by RL. This is the short circuit current, right? Noise squared, divide this by GM squared. This gives you the input referred noise voltage. Now, you should be writing this from memory. I hope I don't have to write this because we have done this a couple of times, several times in the analog ICs course, right? Everybody remembers this? How many of you do not remember this? Good. Okay. So En over En squared. Okay. En squared over delta F is 4 kT gamma by Gm plus RL. What is the other condition now? RL is set. You don't have a choice because the common gate had some gain. RL is set. In fact, GM RL is set. Right? You don't have a choice. Okay. So if you were to write it like this, 4 kT by Gm into gamma plus 1 over, so it is 1 over Gm RL. So I'll write it as RS by RD. Okay. Gamma is a device parameter. RS and RD are set by the common gate LNA. Okay. Of course, RD is under control. It's your design. It's under your control as the designer when you design the common gate LNA. But assume that that has been designed separately. This is what it tells you. What do you have to do? You wanted this auxiliary amplifier to be as low noise as possible. So maximize. Okay. So you need to maximize the GM. What does that mean? Remember, for the input impedance to be not affected, you said the device needs to be very small, but you want maximum GM. What does that mean? You will have to burn a lot of current. Okay. So keep this in mind. You are now trading off broadband noise cancelling capability with burning a lot of current. Okay. Okay. So now to simplify things, I'm not going to draw the cascode. I'll show the circuit without the cascode. You can add the cascode for neutralization. Okay. I'll show the basic circuit. So now we can draw the complete circuit. So I'll call this bias current some I1. This is M1. This is the common gate stage, VB1. Okay. This is the plus side of the circuit. What does the minus side of the circuit look like? This is RL. Okay. This is a common source stage. Okay. I'm not going to show an explicit current source. It is very common in RF circuits not to add explicit current sources. So one big difference between analog circuits and RF circuits, in analog circuits, we spent a lot of time getting a lot of common mode rejection, putting a current source, biasing it very accurately and so on. Okay. In RF circuits, that is of less concern to us. Okay. The reason is we want to maximize the swing. We want to maximize the linearity. Okay. How do you now bias this circuit? Let us say this bias current was I2. How do you bias this circuit? Can I just connect this? So remember, this input needs to go there. Can I just connect it like that? You can't. The reason is this is probably very close to VD sat of this current source. You do not want to over design on that. Because the noise of I1 is going to add to the noise of the LNA. Why would you over this thing, right? Okay. So you want to get maximum swing at the output. So you will design the current source to be as high VDSAT as possible and then give just enough headroom for that. Okay? Okay. What you have to do now is AC couple this. But now you need to bias. I'll call this some VB2. How do you generate VB2? How do you generate VB2? Maybe using a current mirror. Okay. You need to generate a voltage VB2 such that there is a current I2 and M2. Maybe that may be using a current mirror. Okay. The same current mirror which you use to generate I1. Doesn't matter. We know how to do that. Okay. Okay. What is the value of C? We can write it as an infinite cap, but in practice, it is going to be much, much, much smaller than this infinite cap. Why is that? This infinite cap needs to be very small compared to 50 ohms, which you are driving. The input impedance at this node is 50 ohms. The input impedance at this point is capacitive. RB is extremely large. There is a capacitive division between this node and this node in terms of signal voltage. The impedance at the gate of M2 is CGS2. Okay, so you need to make sure C is much, much larger than CGS2, but that's all. No more. Okay. So let us say C is approximately 10 times CGS2, let us say. Okay. So what are our design conditions now? Yes. What if you don't have C? If you don't have C, okay, so if you don't have C, this voltage now, DC voltage will now need to be VB2. What will this voltage be? It will be at 2 VGS. It will be VGS of M2 plus VGS of M1. That can be in, remember, look at M2. We are using a very small device and a very large current. What does that mean for VB2? It is VT plus VDSAT. The current density in M2 is extremely high. Okay, which means VB1 may actually be very high. What will you do if it goes above VDD? Right? You can't do it, which is why it's always better to separate out the bias of the two circuits. Okay? So, don't do this. Don't remove the capacitance. Okay? There are some special cases when you might be able to remove it. I'll put it that way. Of course, one last condition I forgot to mention, which is implicit, it's not explicit. The bandwidth of the common source stage. What limits the bandwidth of the common source stage? Is there a bandwidth limitation at this node? Actually not, because RB is going to be extremely large. Okay, so there is only a capacitive division. If there is a voltage V here, okay, there will be almost V there. So there is a capacitive division. I think I called this V in. If this is V in and this is VG2, and of course you happen to have a large RB here. Okay, for all practical purposes, RB should be chosen so large that across the bandwidth of operation, right, it is extremely large, so that it does not affect it. What does that mean? There is a lower limit caused by RB. Okay. At very low frequencies, the impedance of RB can become smaller than 1 over j omega CGS2. I hope you see that. Does everybody see it? If you choose RB large enough, at higher frequencies, there is no problem. Okay. At lower frequencies, there is a problem. Okay. Because the impedance of the capacitance starts increasing. Okay. Eventually, VG2 by Vin can start becoming smaller at lower frequencies. If you want this to operate all the way down to, let us say, 50 megahertz, 100 megahertz, 10 megahertz, then RB has to be chosen very carefully. If you are interested in operating from 500 megahertz to 2 gigahertz, something like that, no problem at all. Okay, you just choose RB to be of the order of several tens or of kilo ohms, and you're good to go. Okay. Okay. Is it balanced? You're asking if it is balanced. No, it is not. Of course, it is not. For various reasons. First of all, this is not a 50 ohm output. So, okay. I understand the confusion. So maybe I'll put it in quotes. Because it is not a true balance. It is not matched to 50 ohms at the output. Okay. More importantly, the two output impedances are not the same at all. Actually, the two outputs are completely asymmetric. That's what I'm coming to. Okay. The two outputs are completely asymmetric. That is one big problem with this noise cancelling LNA. Okay. So let's look at that now. Huh? Yes. You have to speak a little bit louder because of the... At the input. Yes. If you go to RF frequencies, so let us say RB is mega ohms. If you go to RF frequencies, the impedance of the capacitance, the imaginary part, will be much, much smaller than mega ohms. Right? The actual VG2 by Vin is Z bottom by Z top. So this is Z bottom. So, okay, maybe I'll explicitly write it down. That may make it clearer for you folks. So VG2 by Vin of S, okay, is RB parallel 1 over S CGS2 okay. Let us consider two cases. One case, I move to extremely high frequencies. What do I mean by extremely high frequencies? What I mean is magnitude of RB I move to a frequency, range of frequencies, where the magnitude of RB is much, much larger than 1 over omega CGS2. Okay? What will happen to VG by Vs? It will just become 1 over CGS2 over 1 over CGS2 plus C, right? Excuse me. So this is just C by C plus CGS2. It just becomes a capacitive divider. If I go down very close to DC, RB of course is much, much smaller than 1 over omega CGS2. What happens to Zn? Sorry, what happens to Vg by Vn? Well, it becomes RB by RB plus 1 over magnitude of this, right? So question is, as you go down in frequencies, the capacitive impedance becomes larger of C, even of C becomes larger. Okay, so if you go to frequencies where RB is less than the impedance of both CGS2 and C, this becomes small. Of course, 1 over j omega C is very, very large. So this becomes very small, right? What happens at DC? 0. V out by Vn is 0. I mean, Vg by Vn is 0. Okay. So this is what I mean. If you go to RF frequencies, there's no problem. If you go to baseband frequencies, there is a problem. So even though we said broadband LNA, this is a broadband LNA, but not from DC to RF. It is from some tens of megahertz to RF or hundreds of megahertz to gigahertz. Okay. Does that answer your question? I hope it does. Okay. Now what about the bandwidth limitation at the output? Both sides have a bandwidth limitation at the output, right? What is the bandwidth at the plus node? One over 2 pi RD into drain bulk capacitance of 1 plus the load. If you have a, I'll call that CL1. Okay, let's assume each side also has some capacitive load. So maybe I'll show that in red color here. Hopefully it is symmetrically loaded, but in case it is not, I'll just add CL2 here. So the bandwidth at the plus node is 1 over 2 pi RD into CDB1 plus CL1. In general, are these two the same? So in general, we already know RD is not equal to RL, most probably. Why is that? Huh? GMRL is fixed by ratio of RD to RS. Okay. And remember, for noise of the common source to be very low, GM of the common source should be very high, which means RL is going to be very small in general. Whereas for gain of the common gate to be very high, that is also the gain of the LNA in general, RD should be very high because the gain of is RD by 2RS, right? So in general, RD will be several times larger than RL. Okay. In general, note that the sizes of M1 and M2, the common gate and the common source, will not be the same, right? One is chosen for input match, the other is chosen for noise cancelling. Okay, so what does this tell you? The two outputs are completely asymmetric. That is what this is telling you. Okay, so this is really not a true balance. That's why I went back and put it in quotes. Okay, the output impedances are not the same. The bandwidths are not the same. The only thing you have going for you is that if you take the difference between the two outputs, you have cancellation of noise. Okay. Okay. What happens to the signal? Right? Noise seems to be getting cancelled. What happens to the signal? if you set, okay, so we want to, well, VOD by VS, right? Now that this is broadband, let's assume we are operating somewhere inside the bandwidth of operation, right? So we don't have any frequency constraints. Both of them are broadband sites. So I'm applying some VS, right? Let's assume CGS2 is very small, so that input impedance is 50 ohms. Okay. So Zn is 50 ohms. What does this mean? So GM1 has to be chosen to be equal to 20 millisiemens. Agreed? Okay. By the way, because you are trying to build a broadband LNA, you have the same constraints on the common gate stage also. That you are going to use a very small device with a lot of current, right? Which is why not using that capacitor C is completely untenable. VGS1 and VGS2 are going to be very large. Okay. So you will decide GM1 of 20 millisiemens. This depends on these two parameters. Okay. If you want very broadband range of operation, you choose very large I1, very small W over L. Excuse me. You will choose very large I1 and small W over L of 1. If you are okay with smaller range of operation, then you can trade off in a better way. Okay. If C is 10 times larger than CGS2, you can see that the capacitance in parallel with what you have here, 1 over GM1 you have something like this inside the bandwidth of operation. So the sum of capacitances CGS1 and CGS2 are going to limit your bandwidth. Normally, CGS2 will be several times larger than CGS1 because you need GM to be quite large. Okay, because you need it to be low noise, you will not have a choice. You cannot decrease its size beyond a certain point. Normally, CGS2 will be larger than CGS1. Just keep that in mind, but both of them will matter. Okay. So of course, Vin is now Vs by 2. The current flowing through the common source side is Vs by 2 Rs. That gets multiplied with Rd. So Vo plus. So you have a current flowing upwards into Rd. Times Vs. Okay. What happens through the common source side? Vo minus is basically the drain current 2 times RL with a negative sign. Okay. So what is this? What is ID2? ID2 is nothing but minus GM2 times V in. Yes. You choose capacitance C to be more at least 10 times larger than CGS2, so that if you apply Vn, you'll get almost Vn here. Okay. In general, you'll get slightly smaller, maybe 10% smaller. So you'll have to increase GM further. Okay. So I'll just write it as approximately, if you used an infinite cap, you could get Vn right there. Okay, Vn is Vs by 2. Good thing, the noise is cancelling, but the signal is adding. That's a good part. We have to check this. There is no use if you're cancelling noise and the signal, right? Obviously. Okay. So the good thing is that VOD is plus in fact, because you have chosen the noise to be cancelled such that condition for noise cancellation when I say noise cancellation, I'm cancelling the noise of M1. There's nothing to cancel the noise of M2. Okay, just remember that. Was that RD by RS was equal to GM2 RL. Is that okay? Which means VOD by VS over a fairly broad range of operation is simply RD by RS. This is of course also equal to GM2 RL. Okay. When you take the differential output, both sides have the same gain for signal, same phase for the signals. I mean, opposite phase for the signal, so that when you take the difference, signal is additive. So as you can see in the noise cancelling LNA, the gain through the two paths, the magnitude of the gain through the two paths is the same for the signal portion with the same with opposite signs. For noise, the magnitude of the signal through the noise signal through the two paths is the same with the same sign. Okay, so that when you take the difference, you get additive signal, subtractive noise. Okay, any questions about this noise cancelling LNA? Yes. DC. Yeah, what about DC? Yes, I'm coming to that next. Right, there are still some points to wrap up. We are not 100% done yet. Good point he's bringing up. One more thing you have to remember. Maybe I'll write it down here. What is the DC at the plus node? Is VDD minus I1RD. What is the DC at the negative node? It's VDD minus I2RL. The DCs are completely different. Okay. So if you are going to take this and use it, most probably you will have to AC couple it and then use it. You cannot DC couple this most probably. Okay. Unless you are planning to propagate the asymmetry. Yeah, of course. I just wrote the dominant caps. How do you AC couple? What does that mean? This has two outputs. I add two capacitances in series and then connect to the next circuit. Can you name those other capacitors? CL1 and CL2 are not capacitors that you add. They are the capacitors of the input capacitance of the next circuit. Did I not specify that? CL1 and CL2 are load capacitances. They are the input capacitance of the succeeding circuit. I hope that answers your question. Does it? Okay. I hope it does. Any other questions? Okay. Now, a couple of more things. So, what about, can you cancel noise of RD in this LNA? Is noise of RD and RL cancelled? It's not. Okay. So remember, whatever noise is available at the input node V in can be cancelled. So noise of RD and RL will definitely not be cancelled. You need large gain from the LNA, right? As always, any noise that gets added at the output of the LNA can be improved by reducing the, increasing the gain. So reducing its input referred value. Okay. And that is clearly seen here, where when we wrote down the En squared by delta F for the common source stage, it has a 4 kT by Gm squared RL. Okay. If you increase RL, you decrease the input referred noise. Okay. Increase Gm, increase the input referred noise. Okay. Okay. Now, what about noise of the current source I1? Let us say I1 was an NMOS transistor. It's a current source. I mean, it's a current sink. It is pulling out the current from that node. So I1 is an NMOS transistor, M3. It has some noise IN3. What happens to that noise? Will it get cancelled or not, or will something else happen? Okay. There will be some current IN3. Okay. What will be the voltage V in N due to M3 is half of IN3 times RS, because the total impedance at V in is you have source resistance RS and input resistance RS. Okay. So it is basically, in this case, we are pulling out current. So I'll just show, I'll just show it like this, minus IN3 times RS by 2. Okay. What will happen to this noise? Now, noise is uncorrelated, right? Noise from M3 is uncorrelated with noise from M1. We have already found that noise of M1 gets cancelled. We don't worry about that. What happens to noise of M3? So this noise will now go through two paths, through the common gate stage, through the common source stage.